Hello and welcome back to lesson number 534. In this lesson, we'll be looking at further tricks of solving implicit differentiation. Okay. Here is a question that we want to look at. Consider the equation xy equals 2x minus 3y. You're asked to determine the first derivative and the second derivative. So the first one there is dy by dx, meaning the first derivative, and the second part is d squared y by dx squared, which means you're looking for the second derivative. Now, in the questions that we've done so far, we've looked at equations or relations in which the variables are distinctly by themselves. So x appearing by itself as a term, y appearing as its own term. So this is a term purely in terms of y. This is a term that is purely in terms of x. So we've looked at questions like this. But what happens when you have two variables, x and y, appearing within one term, either multiplied or divided or as a composite function, like this? So in such a case, the third term there has got x multiplied by y. So it is a product of x and y. This is purely x and this is purely y, but this is x appearing together with y. In other words, a product of x and y. So if we're going to solve a question like this implicitly, then again we're going to make use of our understanding from 5.2, which is on methods of differentiation, and in particular this requires us to make use of the product rule. So if we were going to solve this, then that third term there would require a product rule. So we will see how to do that. But it could also be such that the equation has got x and y appearing as a fraction like that. And in this case, because this is a fraction, another term for fraction is quotient, we would use the quotient rule. Okay? And if the relationship appeared as a function within another function. So here we have a quadratic function in the bracket and then a power 5 outside. So that is a function of a function or a composite function. Then in this particular case, we would need to use what we refer to as the chain rule. So if you've looked at 5.2, if you've studied the methods of differentiation, then this should be familiar. The other thing I want us to remember is that when we talk of a second derivative, the second derivative is usually the derivative of the first derivative. That is to say that the derivative of a relation, the second derivative of a relation, is the derivative of the first derivative of that relation. So this, inside the bracket, we have the first derivative. If we differentiate that, we get what we refer to as the second derivative. And so this square that is appearing here on d is referring to this d by that d. So d squared of r. And dx squared, in fact, there should be a bracket here because it's the whole dx being squared, dx and dx, but we don't usually put the square there because anyway what we want to try and do is to use as few symbols as possible, or as to simplify the symbol as much as possible. Anyway, so let's go to the question and try to solve it. We are being asked, the first question was to find the first derivative. So to find the first derivative, we need to remember the idea of a residue that appears when we differentiate y with respect to x. So if we are differentiating, if we want to find dy by dx here, we need to find the derivative of each term separately. So the derivative of x, y, the derivative of that, then that must be equal to the derivative of 2x minus the derivative of 3y. Now, because this is a product, we need the product rule, and the product rule says that the derivative of a u times a v, here we go, so the derivative of u times v with respect to x is you treat u as a constant and differentiate v with respect to x like that, and then you say plus, and now you keep v as the constant and differentiate u with respect to x like that. So that is what we refer to as the product rule. So applying that rule to our question there, the derivative of xy must be, we keep x constant and differentiate y with respect to x. So we're going to get x dy by dx, and then plus y dx by dx, but dx by dx is actually just 1, so we are left with y. And so the differentiating this gives me x dy by dx plus just y. This is y dx by dx, but dx by dx is 1, so that remains as y. Then differentiate the second, the first term on the right. The 2 does not take part in differentiation, so the 2 goes out and we have dx by dx, which is just 1, and so that term becomes 2. Then we differentiate 3y, the same thing we did with this. This gave us 2 dx by dx, so this is going to give us 3 dy by dx, okay? 3 multiplied by dy by dx, and all that is left now is for us to combine the like terms together, and we have that x plus 3, so this move to the other side becomes positive 3 now. So x plus 3 dy by dx is 2 minus y. Okay, and so if we rearrange that, make dy by dx the subject of the formula, we end up with dy by dx is 2 minus y divided by x plus 3. All right, and that is the answer for the first derivative. I've taken liberty to sketch this graph. All right, so when we draw the graph, this is how the graph of this function looks like, and we can try to understand what it means to find dy by dx. Remember, dy by dx refers to the gradient function. So this is the function that we use to find the gradient anywhere on this curve. So for example, at the point where x, at the origin there, if we look at the origin, all right, at the origin, the coordinates are 0, 0. So if we substituted those coordinates 0, 0 onto our derivative function, then we should be able to find the gradient of this curve at the origin. So at the origin, if you substitute 0 for x and 0 for y, we get the gradient to be 2 over 3, which is to tell me that the gradient of the curve at the origin there is going to be 2 over 3. And so if somebody asks me to find the equation of that tangent, that's a tangent there. So the equation of the tangent can now be found because we know the gradient of the tangent. The gradient of the tangent is of course the same as the gradient of the curve at that point. And because we know the gradient and we know one point through which the line is passing, it would be possible for us now to find the equation of that tangent. This question is not about looking for the equation of the tangent, and therefore we can leave this here. We go to the second part of the question, which wants us to determine, I believe, the second derivative. Okay, so we have our first derivative. So if we're going to find the second derivative, this now requires the quotient rule because we have a fraction, right? And so the quotient rule, what does the quotient rule say? The quotient rule, so dy, first of all, remember that the second derivative is the derivative of the first derivative, okay? And so that is going to be the derivative of 2 minus y over x plus 3, all right? And now we need the quotient rule, which says that the derivative of u divided by v is, you start with the denominator there, v, so v times the derivative of u, so v times the derivative of u minus u times the derivative of v, everything divided by v squared, right? So this is something that we already know from the section 5.2. Right, now if we apply that rule into our problem here, then we have that we will have the first one we write v du, so therefore x plus 3, so we're going to have x plus 3 times the derivative of the numerator, then minus 2 minus y times the derivative of the denominator, and everything divided by the square of the denominator, like that. So that's what we have. If we simplify this, this is just going to be x plus 3, the derivative of 2 is 0, the derivative of y is just dy by dx, but it is negative, so we'll have negative of x plus 3 dy by dx, like that. Negative of x plus 3 dy by dx, and let's look at the second term there. So we have minus into bracket 2 minus y, the derivative of x is 1, and the derivative of 3 is 0, the derivative of a constant is 0. So this result here gives us 1, and so it's just going to be minus into bracket 2 minus y, which is the same as minus 2 plus y. The negative turns the negative y into positive y. So it's minus 2 plus y divided by x plus 3 squared. All right, we can simplify that a little further by dividing. So if we divide this by that and this by this, what do we end up with? We can write y minus 2 instead of minus 2 plus y, and then divide there. Please remember that a plus b over c is just a over c plus b over c. So if we make use of that fact, it makes life easier. And so that gives me d squared y by dx squared becomes, so I will start with this. So this becomes y minus 2 divided by x plus 3 squared, and then it's going to be minus, but this goes with one of them, and now we have negative 1 over x plus 3 dy by dx, like that. All right, we have found the second derivative, except that we already know what dy by dx is, so we could put this here and to replace dy by dx. So in place of this dy by dx here, I'm going to remove it and replace that, right? So we can substitute 2 minus y over x plus 3, and now if you look at this term here, it is exactly the same as that term. All right, so that term there, if you look at it carefully, it is effectively the same as y minus 2 over x plus 3 squared. And so it's the same as that, and because we are adding them, we end up with twice y minus 2 over x plus 3 everything squared. So this is the second derivative, and by the way, in this case, it is possible to make y the subject of the formula. It's possible to write this explicitly, and because of that, we could replace the y here so that the second derivative is purely in terms of x. But we don't really need to do that because when in these questions, usually you will want to determine the values of x and y, and sometimes it's better to leave it in this form. Okay? And so that is the second derivative on this problem. Okay? Thank you very much. See you in the next video.